Hello! Today what I'm going to do is an energy problem that's a little more difficult, and I'm going to show you how to do it two different ways, both equally valid. They get you the same answer. One is a little more work, maybe. So we have a hard energy problem. A 10-kilogram sled starts on a slippery slope that is 20 meters long at an angle of 8 degrees. If it starts at rest at the top of the slope, goes down the slope with a coefficient of friction of 0.10, then coasts on flat ground with a coefficient of friction of 0.20, how far along the flat ground does it go? There's our problem. Okay, we're going to start with our picture, and we have a sled going down a slope and then onto a flat. And I'm saying there's a person. Oh, that's really a weird person, isn't it? They're leaning down. Yeah, that looks good. Oh, nope, velocity equals 0 here. And then they're going to come down here, and then they're going to scoot along here and come to rest. So there's our at rest, and at this point we're moving. Yeah, not a great picture. It's okay. We have an 8-degree slope. Okay, so my angle was 8 degrees. The mass of the sled was 10 kilograms. And the length is 20 meters, so you can call that what you want. The length of the hill, length of the slope, is 20 meters. And the coefficient of friction on the slope, on the hill, I'm being inconsistent. Let's see. The slope is the hill. Mu on the hill is 0.10. Coefficient of friction on the flat ground is 0.20, twice that. We want to know the distance along the flat. How far along the flat does it go? All right, picture, knowns, unknown. And here is where, as an energy problem, we typically do initial and final. And I'm going to do it the longer way first. That probably will make more sense for people. I'm going to break it up into two chunks. So I'm going to say this is my first chunk. I'm going to start at rest at the top of the slope, and I'm going to go down to the base of the slope. So I'm going to call that my first one. So initial is up here, and my final is right here when it's moving downward. And then after that, I will say, okay, I'm going to say initial here and final here. So two separate steps. Okay, initial to final. Let's see what we've got. Initial energy plus minus work equals final energy. Initial energy, three different types we could have: kinetic, potential due to gravity, and potential due to a spring. And then we've got the potential to do work, and then those three, Ke plus Peg plus spring. Okay, so at the top in our initial, do we have any of these three? And the questions to ask yourself: kinetic energy, is something moving? In this case, no. We have no kinetic energy. Nothing there. Is something above its lowest point? Well, yeah, we end down, we start up. We do have potential due to gravity. Is a spring compressed or extended? Well, I don't see a spring in this problem, so I'm not going to worry about spring energy. At the final point, in the final condition, when we're down here, is something moving? Yeah, the sled is moving, so we definitely have kinetic energy. Are we above our lowest point? No, we're at the lowest point, so we don't have gravitational energy. So now we start with potential energy due to gravity, and we're going to end with kinetic energy. Is anything doing work? Are there any work terms? To figure that out, we have to look at the forces acting during the two and then compare it to the direction of the motion. So as it's moving down slope, we've got our weight, our normal, friction, a small friction force, and there's nothing pushing it forward, it's just sliding down. So we've got that. The direction of motion is this way. So our direction of motion is this way. Work is only done when a force is parallel to the direction of motion. And what I like to do, oh boy, is take something, we'll take this, and line it up with the direction of motion, and then look at all your forces. Are any of these parallel to the direction of motion? Well, N is perpendicular, so there's no work done by the normal force. Friction definitely does work. That's definitely parallel. It's anti-parallel. And then we've got the weight, but that has two components. I'm going to be careful. I'm going to do mg here because I've got a w there and a w there. All right, there's a perpendicular term to my distance, and then there's also a parallel term. So you might say that there's work done by gravity, by the weight. But the work done by gravity, that's right here. We've taken that into account already. So we've already dealt with gravity. We don't add that into our work at all because it's taken into account right there. Which means the only thing doing work is the work done by friction. And because it's anti-parallel, they're opposite directions, it's negative work. And that should make sense that work done by friction is taking away energy. It's removing energy from the system. We now have our equation. All right, so from up top to the bottom of the slope, we know what's going on. PEG is mass times gravity times height. The work done by friction is friction times distance. KE, 1/2 mv squared. What do we know? All right, we know the mass. We know acceleration due to gravity. The distance traveled, we know the mass, and okay, we need a little more information here. Height, do we know the starting height? Well, we can get that because we know we went 20 meters down slope, and this is at an angle of 8 degrees. So our height is going to end up being the distance times the sine of our angle. And if you do that, you should get a height of 2.78 meters. So even though you're going 20 meters down slope, your total height distance is a little less than 3 meters. All right, so we've got our height. This is kind of what we're going to look for, I'm thinking. If we know our velocity at this point, that'll help figure out the distance traveled. So I'm going to say this is what we're looking for, which means we need to figure out friction. Okay, how can we figure out friction? Well, friction is mu times n. So this term is going to be mu times n. Don't lose this distance. It's important. All right, I know mu. I've got mu for the hill. I need my normal force. In order to get my normal force, I'm going to look back at my force diagram and say, can I figure out what the normal force is? There is no acceleration along the perpendicular here. There's nothing making it accelerate away from the slope or into the slope, which means that this force, the normal force upwards, has to be exactly equal to this part of the weight downward. Which component of the weight is that? Well, this is our angle. Remember, if we draw our triangle dropping down from normal, this is the same as the angle of the slope of the hill. So this piece right here, adjacent to the angle, my normal force has to be exactly equal to this, which is my cosine component of the weight. So normal is my weight cosine theta times d. Again, don't lose that d. Do I know everything? I know mu, I know m, I know g, I know my angle, and I know my distance. Okay, at this point we can solve for what our final velocity is. We have everything ready to go. So my first term is mgh, my middle term is mu mg cosine theta times d equals 1/2 mv squared. And I'm looking for this right here. I know everything else. Please note that there's a mass in every term. The same mass in every term. We have 3 terms, there's mass in each one, which means we could cancel it. You don't have to, because we do know it in this case, but just to make your punching buttons life easier, you can get rid of that. And if you do this, you should end up with a velocity of 3.96 meters per second at the base of the hill. 4 meters per second, about 8-9 miles an hour, that's totally reasonable with very, very little friction. So now we've done this portion of our problem, and we know how fast the sled is going at the base of the hill. So that's part 1. Now I'm going to do part 2, where we go from the base of the hill till the point where we end and have come to a rest because of friction. So let's see what we've got here. I can erase all this pretty much because I think it's going to be different. And if you're having trouble with, what kinds of energy are where, feel free to, on your equation sheet, write down for each of the types of energy what the question is that you ask. Kinetic energy is something moving. Potential energy due to gravity is something above its lowest point. Spring energy is a spring compressed or extended. So that's something that you can always take advantage of. And we no longer have this as our force diagram. Okay, initial to final. What do we have? We've got our three types. We could start with kinetic or gravitation or spring energy, and then we could have work done. We can end with kinetic or gravitational or spring energy. And again, there's no spring in this problem, so no spring energy. I should put spring. There we go. Are we moving at the first condition? Absolutely. Are we above our lowest point? No, we don't change height at all. Okay, not that. Are we moving at the end point? No, we come to a rest. That's the question. How far along the flat ground does it go? It comes to a stop. So we don't have kinetic. Are we above our lowest point? No. No potential energy. All right, so we start with kinetic energy. What kind of work do we have, if any? What's the force diagram for between here and here? We have mg going down, got our normal going up, friction slowing us down. That's it. What's our direction of motion? The direction of motion is this way. So, what's parallel to our direction of motion? Normal? No. Weight? No. Only the friction. Which means we have one work term, and that is work done by friction, and it's negative because that's going that way, that's anti-parallel. What kind of energy do we have to end with? Well, that's a very exciting equation. Kinetic energy minus the work done by friction equals 0. We end with no energy. That's quite possible. Sledding is hard work. You end up with no energy. Which means kinetic equals the work done by friction. 1/2 mv squared equals friction times distance. We know our mass, and we had our velocity from before, so I should write that down. Our velocity was 3.96. What was our velocity? Yep, 3.96 at this point. Meters per second. So right here. We don't know our friction, and this is what we're looking for. This is our question mark. Okay, we know that, we know that. We need the friction. Same process. Friction is mu times n. What's our normal force? Well, in this case, go back to the force diagram. The normal force up has to equal the downward force. This is a straightforward normal equals weight. So 1/2 mv squared equals mu mg times the distance. And we are looking for this right here. Again, two terms, mass in each. So 1/2 velocity squared equals mu times g times our distance. And if you do the math, you get a distance of 4 meters. Is that reasonable? Well, if you're doing about 4 meters per second, so about 9 miles an hour, and then you have a little bit more friction now, going 4 meters on the flat, sure. Seems like, if it was 40, I'd wonder, and if it was 0.4, I'd wonder, but 4 meters seems quite reasonable. All right, so we have a reasonable answer. Did we answer the question? How far along the flat ground does it go? We did answer the question. It goes 4 meters along the flat ground because we said this was our initial point and it went 4 meters from that initial point. Okay, so this is how to do this one in 2 steps. You can also do it in 1 step if you want. It's got the same kind of setup. I'm going to get rid of this. Okay. That's all true, that's all true. But what do we have going on here now? While I'm erasing, think about what would be the energy equation, so like this kind of equation, if we go from the top all the way to the bottom. So see if you can come up with that while I'm erasing. So we're going to go from the very top all the way to the bottom, just one step. And the initial energy and the final energy you can probably figure out pretty easily. It's that work thing that's the hard part for this one. La, 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 la. Okay. There we go. All right. Now, what do we have? We are going to go all the way from here. So our initial is here, our final is here. What kind of initial energy do we have? Is it moving? Yes. No. No, it's not. It was moving here. Not kinetic energy. Is it above its lowest point? Yeah, so we do have PEG. No spring. Plus or minus the work equals final energy. Is it moving? No. Is it above? No. Is spring? No. All right, so we need to figure out what type of work is happening. And here is where we have to do kind of the both steps from before, but we have to treat them separately. There's work done here by friction, and there's work done here by friction. So to figure out the work, I have to do both pieces. I've got weight, I've got normal and friction, and then on the flat, I've got weight, normal, and friction. My distance traveled, or direction of travel, is here and here. So I have to take into account both the angle and the flat. I do exactly the same process that I just did a few moments ago. The only thing doing work here is the friction force. The only work doing here is from the friction force. Which means we end up with PEG, we start with gravitational potential, and we've got a negative work done by friction on the hill, and a negative work done by friction on the flat, and that leaves us with no energy at the very end. mgh, initial height, minus friction up the hill times the distance on the hill, minus friction on the flat times the distance on the flat equals 0. What do we know? We know the mass, we know gravity, we can figure out the height just like we did here. We know the distance traveled along the hill, that was our 20 meters. The distance along the flat, that's what we're looking for, this is our question mark. We need to know what the friction is on the hill and what the friction is on the flat. Doing exactly the same process that I did just a few moments ago, what you should end up with is, let's see, on the hill it'll be mu times the normal, and the normal is the cosine component times the distance on the hill minus the friction on the flat, which is mu times the normal, which is just the weight here, mg, times the distance on the flat, equals 0. We know everything here except for the distance on the flat. And if you want to make your calculating life a little bit easier, take a look at what we can get rid of here. mg, mg, mg. This looks much easier if you do it like this. Okay, h mu cosine theta times d hill minus mu d flat. D flat, like the note. Oh, I better be careful. This is on the flat and this is on the hill. We had two different coefficients of friction. We can do the math. We know absolutely everything. And if you do, you get, what a surprise, 4 meters. So we come up with exactly the same answer, doing it in one step from here all the way down to there, or doing it in 2 steps, top to the bottom of the hill, from the beginning of the flat to the end of the flat. They're both perfectly legitimate, and I don't care which way you do it. You can go whichever way makes more sense to you. If breaking it into 2 steps works better for you, do that. If you can see that if I go from here to here, I've got to deal with 2 different work, the possibilities of 2 different terms for work, then do it in 1 step, and you'll be fine. So we've got a reasonable answer, we answered it, and I showed you how to do it in 2 different ways. So there you go. This is a moderately hard energy problem. So this would be close to an A-level energy problem because we have quite a bit going on. We've got quite a bit going on, including 2 different coefficients of friction. We've got the angle and the flat. Lots happening here. You had to figure out the height. And well, that's it. Yeah, so there are 2 different ways to do a hard energy problem. All right, good job.